When I put this problem together for today that we actually finished the other handout. So I just wanted to give you some more practice. So the concept here is you look at the first sheet, again, is you've got to find the points of intersection for the three lines. So they're going to be 3 points. So you'll need to set each of them equal to each other, to the other ones. And I made it so that the points of intersection are actually whole numbers instead of fractions. Also on the first page, I want you to take the 3 equations and solve them so they're, instead of y as a function of x, to solve them as x as a function of y. Now the last equation, y equals x over 4 plus 9/4 x, the easiest thing to do there is just to multiply everything by 4 initially to get rid of any fractions. So there you go. You can do the first part, and then we'll go to the next. Once everybody gets the points of intersection, then we'll continue on from that point. But there's no point in going if you don't have the right points of intersection. So I think I get my new trumpet today. I'm excited. So does anybody like Coldplay? Any Coldplay fans here? You know the song Viva La Vida? Yeah. Well, we're going to play our band. I saw that online. So our brass quintet is going to play it. It's a really cool arrangement. I was going to play it for you this morning, but the speaker thing doesn't work. So I'll have to wait till tomorrow to hear the arrangement. It's pretty. Oh, did they?
Really cool.
Yeah, yeah, it is. They kind of switch between the different parts for the melody. So the trombone has the melody, and then the second trumpet has the melody, then the first trumpet, and then the horn, French horn. So that's good. I've been singing it to myself. Da 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 ba ba ba. So there's one for you if you've forgotten how to do it. So the blue curve is, or the red curve is y equals x, and the blue curve is 4x minus 24. So when you solve those, set those equal to each other, you get x equals 8, and then you can plug back into one of the 2 equations, either one, and you get the second point. And you can see it's 8, comma 8. Yeah, and if you finish the first page, which is calculating the points of intersection, you can go to the second page and start if you feel confident in knowing what you're doing. So the first one is to do the washer and the washer method around the x-axis and the shell method around the y-axis. And then this third page is solving using the washer method around the y-axis and the shell method around the x-axis. But if you're not so sure, you can wait. I think it's my trumpet's the most expensive thing I've ever bought for myself. Okay, so those are the 3 points. So if we set x equal to x divided by 4 plus 9/4, you multiply it by 4, so you get 4x is equal to x plus 9, subtract x from both sides, you get 3x equals 9, divide by 3, you get x equals 3, plug back into this one, y equals x, you get y equals 3, and you see that's that point. And then finally you set the blue and the green equal to each other. Again, I multiplied by 4 to get rid of the fractions. So 16x minus 1x is 15x. 96 plus 9 is 105. 105 divided by 15 is 7. So that's x equals 7. And then I plugged it into y equals 4x minus 24, which is this point. Okay, so those we're going to use those for our limits. And the next thing is to rewrite the 3 equations in terms of the other way around. This one's the easy one. Okay. So if you haven't done the other 2, go ahead and do those now. So you'll just just solve for x in both cases. So we'll need those later. So anyway, so going to the next part. Let me copy this thing. So both of these are going to use vertical rectangles. So I'm going to draw some rectangles here. And I'm going to draw two of them because you'll see that there are two parts that we have to worry about. So in contrast to the previous problem, the bottom curve changes, but the top curve stays the same from this perspective. So I've used vertical rectangles. So that'll give me a washer if I rotate around the x-axis, and it'll give me a shell if I rotate around the y-axis. But they're both integrating with respect to x. And the curves that define the top and the bottom of the rectangle are the same for the same intervals. So you can see that the x limit is going to go from 3 to 7, and then from 7 to 8. And then the curve on the top, which is the red curve, defines the outside radius of the washer. And the green curve for the first interval defines the inside radius. And then for the second interval, the blue curve represents the inside radius. Now when you do the shell method, instead of squaring the things, because it's not pi r squared, it's going to be the length of the rectangle is the height of the shell. So what I'll do is I'll write down on the next page, I'll write down the equations that you don't have to memorize, but you're going to have to figure out how to. So if we do the washer method around the x-axis, the volume equals pi times the integral from a to b of r of x squared minus little r of x squared times dx. And using the shell method around the y-axis, the volume is equal to 2 pi times the integral from a to b of p of x times h of x times dx. So you're going to have two integrals for each interval, from 3 to 7, 7 to 8. The outside radius is always going to be the same. It's the red curve. The inside radius changes from the green curve to the blue curve. And then for the shell method, if you're rotating around the y-axis, this p of x is just equal to x, and h of x is just the difference between the two functions, the one that defines the top of the rectangle and the bottom of the rectangle. So you're going to have stuff squared in the top one, you're not going to have stuff squared in the bottom one. So I know some of you are just waiting for me to write it out. You're like, why should I do this? But the problem is that if you don't do it yourself, you're not going to know what the heck you're doing. So you're only shortchanging yourself if you are being lazy and just decide to wait. So let me just write the equations. Y equals x is the red curve. The green curve is y equals x over 4 plus 9/4. The blue curve is y equals 4x minus 24. So I've even showed you what they are here. That's your outside radius. That's the distance from the x-axis to the closest part of the rectangle, which is the green curve for the first interval and the blue curve for the second interval. And the outside radius is the curve that's furthest away from the axis, which is the red curve. And I've got the answers, so I can come around, and if anybody's, I think Evan's got an answer, so I'll check his answer, I think. Have you gotten the answer yet?
You want to like
Oh,
evaluate it?
no, I just want you to come up with the equation. So that looks right. You just have to do the second part. Yeah, so I don't want you to evaluate it. I just want you to set it up. We might evaluate one of them. I don't want to do all 4 of them, all 8 integrals. So I'll give you the first part of the first answer. You can think about what it is if you're... So if you don't understand why I did that, raise your hand. Okay. I'll come and sit between you. Yeah, that's just algebra. Yeah, so what you're looking for, what you have these little discs. They're not discs because they don't go all the way to the axis, but you got this little material and you rotate it around the x-axis. So you create washers. And the equation says you take the outside radius of the washer. So if you take the distance from the x-axis to here, that's the radius to the outside. So you see which curve corresponds to that part. Well, that's the red, that's this curve. So R of x, that's why I put capital R of x as being this curve. Now, the inside of the washer is running up against this curve. So that's your inside radius, because that's the smallest distance from the x-axis to this curve. So that's why I had this curve here is x over 4 plus 9/4. So you use the equation to define that, because as you move along, the radiuses are changing. So you know it's not a constant thing; it's a variable thing.
We're supposed to kind of picture a washer, which is kind of like
Right. Yeah. So if you tried to do this, you could imagine this thing going around like this in 3 dimensions. So it's kind of hard to draw it because it's but you'd have a washer that went out this way, comes out, goes in, and loops all around. So this little rectangular thing, it's kind of like this coming out like that. So here's the let's say this is the x-axis. So what happens, this thing rotates around the x-axis. So the distance from here to the x-axis stays constant, and then it loops down underneath here, and then it come back up through the table, and then come back up and go like that. So that's what the washer, if you instead of just being a line, if it went all the way around, you'd have something that looks like that. Because if you look at the side, that's what you're looking at there. The side looks like 2 circles, where the inside radius is of the circle, this thing, is this point, and the outside radius is that point. Okay, so we're just taking those washers and then we're stacking them up this way. So it's like we're putting them together here. So the washer goes around this way, but you're stacking them up. And so these are like little infinitesimally thick washers. And each washer has an outside radius and an inside radius. And by integrating it with respect to x, we're basically adding all those washers up. And the reason we change to this function is because when you get to this value, x, the inside is no longer this curve, but it's that curve. So in the second part, when you integrate from x equals 7 to 8, this is x equals 7, this has x equals 8, then you use this curve as the inside radius. But this one still stays the same because it's the outside radius is the same. Okay, does that make more sense?
Yeah.
Why don't you explain to Zane, and that way he'll give you a chance to, so you think about it, I'll let you explain it, and that way.
So how do we figure out what P of X is, like when we're working on it?
P of X is always X if it's rotated around the Y-axis.
Okay.
But if it's not, it's something else, and I'll explain that. But for right now, we're just doing it around the X and Y-axis.
So it'll all be, right now it's X.
And right now it's X, yeah. Okay, let me give you the second half of the problem answer. So, this part is dealing with this rectangle. As you move it, as it moves horizontally, so let's say it moves here, you notice that what I'm really doing here, by integrating with respect to x, I'm stacking all these washers up next to each other. And each washer is defined by the red curve being the outside radius and the blue curve, the green curve being the inside radius. But at some point, once I do this, I run to this point. And that's why that limit is 7. Because I started out here at 3. I had all these little rectangles which, when rotated around the x-axis, become washers. Okay, so that's what we're doing here. Now when I get to this point, now the inside radius is the blue curve, so I integrate from 7 to 8, because that's the x value where that change occurs. The outside radius is still x, y equals x, the curve y equals x. So that's where that comes from. And then you subtract what defines the inside of the radius, which is 4x minus 24. And you square that, and you multiply it by dx. So that's the answer for using the washer method. Now, when you do the shell method, now you're rotating around the y-axis. So instead of having a really thin washer, you're going to have a shell this way, a shell that has a very thin thickness to it, but it does have a finite height to it, which are the height of the rectangles. So in that case, the only thing, the limits stay the same, the equations that define the boundaries stay the same, but the equation we use is different. So we'd have 2 pi times the integral from 3 to 7, same limits. P of x is x. So this x comes from the fact that anytime you rotate around the y-axis using the shell method, that's the value that you use. So that's where that comes from. It's not because of this equation, it's because of that requirement. And then you have the height of this rectangle, which here we're taking the squares because we're taking the difference between two circles. Here we're taking the actual height. So all we do is we take the difference between these two functions, the upper curve, which is the red curve for the first part, and the lower curve, which is the green curve. And then you multiply by dx. So if you haven't already done it, I'll give you a minute to figure out what the second part should be based on looking at what we did for the second part of the interval using the washer method. We still have x, because that's, and the reason it's x is because that's for each shell, the x distance to that shell is the radius of the shell. Now I'm going to point out what happens if you are rotating around something different than the x-axis, and I mean the y-axis in this case. And once we finish this second little bit here. Okay, so that's the second part. This x is because p of x is x when you rotate around the y-axis. This x is because y equals x defines the one boundary of the rectangle. And then you subtract the lower boundary, which for this interval is the blue curve and not the green curve. Okay, so let me introduce this concept of what would happen if I rotated around something other than the y-axis. So let's, I'm going to add a page. So what would happen if instead of rotating around the y-axis, I rotated around the line x equals 10. So let me just draw that line, because the y-axis is x equals 0. So that's the y-axis is the same as the vertical line x equals 0. And oh yeah, I need to draw my line. So I'll make that a color. What's a good color? We already used in blue. So here's x equals 10. So instead of rotating it around this way, I rotate it around this thing. So now the shells are going to go like this instead of going like that. So let me see if I can at least get one person to give me the right answer here. So let me get rid of a lot of those rectangles in there. I just need one. Okay. So what we did here is we said p of x equals x. So that's the distance from the x-axis. So what we're doing when we rotate around the vertical line x equals 10 is we are, p of x now becomes this distance. So then if this is p of x when rotating around the y-axis is x, then what is p of x when you rotate around x equals 10? I'll ask Daniel because he was asking me about that.
10 minus x.
Exactly, yeah. So it's 10 minus x. Okay. So when you rotate around an axis other than the other than the y-axis using the shell method, all you have to do is take the x value that you rotate around, which in this case is 10, and subtract x. So if I rotated around a line, vertical line, x equals 12, p of x would be 12 minus x. If I rotated around a line, x equals 15, p of x would be 15 minus x. It's whatever it is. Now you can't rotate around here because then it's in the middle of the areas and you have to do something different. But if it's outside of the area of interest, which it always will be if for problems that I give you, it's always just going to be that x value minus p of x will be that. So if I look at my solutions here from my previous one, so if we come down here and we say, how do these equations change by rotating around a vertical line of x equals 10 instead of x equals 0, the answer is going to be 2 pi times the integral from 3 to 7 of 10 minus x times x minus x over 4 plus 9/4 times dx plus 2 pi times the integral from 7 to 8 of 10 minus x times x minus 4x minus 24 dx. So the only thing that changes, that's the sweet thing about when you're using the shell method, if you change the axis of rotation to some other vertical line, the only thing that changes is one term. Now, if you did it with the washer method, it becomes much more, it gets, I mean, it's not that much more it is more complicated. Okay. Here it's not very complicated. I'll show you how to do the other one, but I'm not going to do it right now. I don't want to make your brain explode or anything like that. Okay. And why is this? Because the radius changes with the where you're rotating around, because your function that define, or the x still defines where the rectangle is, but where that rectangle is relative to the point of rotation changes. And that's reflected in that term. But the height of the rectangle isn't dependent upon where you rotate the rectangle around. So that's why this doesn't change, and this does change. Okay, so let's go to the next page. So now we're going to do the same thing, but we're going to go the other orientation. So let me grab a copy of this thing. So now what we're going to do is, instead of having vertical rectangles, we're going to have horizontal rectangles. So when you rotate around the x-axis, now you're going to have shells. You're going to have a thin shell. As this thing rotates around, you're going to have a thin shell like this. So think of the rectangles as being infinitely small, and it's going to rotate around the x-axis, and it's going to make a shell. The width of the shell is the width of my paper here. The thickness is really small. Okay, so you can think of it as a really thin pipe, or you can think of it as like this. If I take this paper and make it into a tube, that's what I'm basically doing here, is I'm creating little tubes, and I'm stacking those tubes inside of each other, or outside of each other. So in that case, if I look at rotate around x-axis using shell, and the equation is 2 pi times the integral from c to d of p of y times h of y times dy. And if I rotate around the y-axis, now they're going to be washers around the y-axis. So you got these going around. So now what happens is this rectangle rotates around the y-axis like this, and it creates a washer. So it's kind of, the washers are going to be stacked on top of each other. And the volume is equal to pi times the integral from c to d of r of y, capital R of y squared minus small r of y squared times dy. And we've already figured out the equation, so I'm going to write them down here in different colors. So the red curve is x equals y. The blue curve is x equals y over 4 plus 6. Is that right? Yeah, because it intersects the x-axis 6, so that makes sense. And the green curve is x equals y over 4. I just did that one. It's not that one. It's the other one. 4y minus 9. And if you followed the green curve, it would intersect the x-axis at negative 9. So those are the different curves. So, you know, doing the shell method, you can see that for part of the interval, the red curve is on the bottom. The red curve is always going to be on the bottom because that's the curve closest to my axis of rotation. And the top curve, for part of the interval, it's the green curve, and for part of the interval, it's the blue curve. And you have to use the y limits in this case, not the x limits. So if you look at the y coordinates of the points of intersection, if you go back to the first page again, you'll see that this is at 3. So that's going to be the lower limit. Then I go here, which is 4. And then I go up to here, which is 8. So I'm going to integrate from 3 to 4 and from 4 to 8. From 3 to 4, the green curve is the outside curve and the red curve is the inside curve. From 4 to 8, the blue curve is the outside curve and the inside curve is the red curve. Inside curve is the red curve. And P of y is y. Okay. And that's because we're rotating around the x-axis, just like the other case when we rotate around the y-axis, P of x was x. So you should end up with something squared minus something squared here, whereas up there you'll have just something minus something. You know, you should see that correspondence. What time do we have? Yeah, we should be able to finish this. We may. Hey, I figured out why our LEDs didn't light on last Wednesday. I'll tell you tomorrow. Keep you in suspense. Okay, I'll come back and talk to Zane now. Okay, so let's look at what's going on here. Let me borrow your pen.
I think I'm getting there.
Yeah, it takes a while, but so you got this rectangle, and the washer. What you're doing is you're rotating this washer out here around like that. So if I draw a line here, this is the first thing it hits. So that's R. That's the small. That's the inside radius. And then if I draw out here, that's where it bumps into the outside. That's capital R of Y. So you just have to figure out, you have to find the equation for this outside radius, which is the green curve, right? So the green curve says it's 4y minus 9. So that's going to be your capital R of Y. And then you look at the other one. The inside curve is the red curve, which is what x equals y. So this is going to be y. Okay. Now when you do h of y, instead of squaring them, you're just going to have this value minus that value instead of this value squared minus that value. Okay. When I did that career switcher program, so I could get qualified to teach high school since I wasn't qualified earlier, but I did observations in the person who used to teach calculus at Allegheny, Mrs. Hicklin, and the thing they were covering the time I was in there was this concept, and I remember struggling with it initially. So but there is a point where again it kind of clicks. Hopefully, part of it is just visualizing what's going on. What's a washer look like? What's the shell look like? And I think, for me it's obvious because I've done it so many times, but I think there'll be some point where hopefully it'll, which is good for calculus, but it's also just good for visualization of things. If you ever become an engineer, that's something that is an important skill. Speaking of engineers, so Elena, she's gone to tech. She was originally in engineering. I was talking to Allison Fox yesterday. She says, "Oh, I saw Elena." I said, "Oh, she's still in engineering." And she says, "Well, I think she might change to dentistry or something like that." And one comment she made was that she could only understand half of her professors that she had. You find that out, especially if you go into a technical field. I think it's even worse now than it was when I was there. A lot of the people who are professors are foreign born and they aren't English. English is not their first language. And when you're dealing with something that's complicated like calculus or physics, and then you can't understand the guy either, that becomes an issue. Why does that happen? Yeah, that's a good question. I know the answer. It's not the greatest answer, but okay. Let's see what we got here. So 2 pi. So we have two integrals. We integrate from 3 to 4. P of y is y. H of y is going to be the green curve minus the red curve, because that's the inside. Then for the second part of the interval, you've got the blue and the red curve. So you integrate from 4 to 8. So P of y is still y. The outside curve is now the blue curve, which is y over 4 plus 6. And the inside curve is still x equals y. And that's it. Anybody got any questions about that? You're like, oh, it looks so easy when you do it. So you can kind of figure out what the next, even if you didn't know what you were doing, you could almost figure it out just by looking between these two. So you're still going to have the same limits, 3 to 4. This is now the outside radius instead of the outside, defining the outside position. So you get 4y minus 9 quantity squared. That's your outside radius. And your inside radius is y. So you square that. And you multiply by dy. And then the second part is pi times the integral from 4 to 8. And this now defines the outside radius. So I square that, subtract the inside radius, square that, multiply by dy. Okay. So I'm going to hand another thing out today. So now we're going to do some other problems, but they're not straight lines, they're curved lines. Or some straight lines, some curved lines. But maybe with your experience now with the straight lines, you'll be able to understand the curved lines better when we get to that point. And you can, what's that? Professional day. Okay. I stole somebody's copies apparently. From this exercise we can see maybe an advantage sometimes to using one method over the other, even though we could use either method, the shell method or the shell method or the washer method. The integrals may be slightly easier, but they're not that much different. We'll find in some cases that you can only really use one method. Or one method is way easier than the other method. So we're going to talk about that. Not yet, but. So let's see what it says. Set up the equations for calculating the volume by rotating the area around the x-axis using the washer method. So I'll sketch this, and I want you to draw your rectangle that you think you should use based on what we just did. So look at your one we just did. Look at rotating using the washer method around the x-axis. See what kind of rectangle you think the rectangle should look like. And the curves are y equals 13, x equals 0, and y equals x squared plus 4. So those are the four curves. And we're rotating this area around the x-axis. So draw a rectangle. See if anybody's drawing the rectangles in there yet. Okay, so it should look like that. So once you have that, then go back and look at what equation we used for rotating a washer around the x-axis without any numbers in it, just the general form like this thing. So go back and look at what we just did. So look for the words washer around the x-axis, and then find which one of those, one was the washer around the x-axis, one was the shell around the y-axis. So just write that equation down. Okay, so that's the one you should have picked. Okay, notice we're integrating with respect to x because we're going to stack those washers up in the x direction. So now all we have to do is figure out what are the functions that define the inside radius and the outside radius. In this case, there's no two parts, it's just one integral. So it's going to be, that's always the confusing thing, because you think r of x and then you look and see the equation y, but it's f of x equals y, so it's just, so you're looking for the equation y equals some function of x. So what is the outside radius? I'll ask somebody this question. So let's see, Kelly. So what is the equation for the outside radius? Well, so look at the rectangle. Which is the part of the rectangle that's furthest away from the x-axis? Which line? Yeah. Okay. So that's the answer. It's the one that's furthest away. So capital R of x is just 13. And you got the answer for the second part of the problem. The inside radius is the part of the rectangle that's the closest to the y-axis. I mean to the x-axis. So in our case, in this particular case, and this is, we haven't had the case where you have a straight line, so it seems kind of weird, but so for our case, R of x equals 13. The outside radius is a constant. And small r of x is x squared plus 4. Now we need to figure out what the x limits of integration are. So let's see if we can figure that one out. And the point where the two curves intersect is, what is that? X equals 3. So, Cassie. So what do you think the x limits of integration would be? Yep, good. So there's 0 and 3. There's 0 because that rectangle, the left part of the area is defined by x equals 0, and the right part of the area is defined by the intersection of the two curves. So, and the two curves, they intersect at x equals 3. So we can say a equals 0, b equals 3. Therefore, the volume is equal to pi times the integral from 0 to 3 of 13 squared minus x squared minus 4 squared times dx. And that's it. So to get the answer, you just have to multiply out. Square this, square that, combine like terms, integrate a polynomial, and plug the numbers in. Okay. So what we'll do next time is we'll move on to the next problem, which is using the shell method around the x-axis. And then we'll do so we're going to do all the different kinds again. We'll wait for that. But go ahead and keep your papers for right now, because you can use those kind of as a reference. Oh, and if I haven't already done it, let me put up 7.3 homework. Did I do that yet or not? Yeah, okay. So we're not assigning any new homework for a while.